All right, here we are. Going to do a lesson on continuity and IVT. Remember what that stands for is the intermediate value theorem. This is like one of the first things that we did this year. So we're going way back, and I'm doing it on purpose to go back to what did we do first, and then kind of move forward from there. Will these be on the AP exam this year? I think so. I think there will be some kind of question about continuity or the intermediate value theorem. I think that this is the first thing that maybe even before limits, because you can use limits within this. So I think there'll be something on this. I think there's a pretty good chance of it. So let's talk first about the definition of continuity. Now, one of the things that, we can talk about the definition of continuity in pretty basic terms is when you look at a graph, does it have any breaks in the graph? A continuous graph doesn't have any holes, jumps, or asymptotes. So we know what it looks like, but I think the big thing is how do you define it? And here's what you really need to look at. F of x, which is just generic, is continuous if the following is true for all x on some interval, a to b. It could be on an interval from negative infinity to infinity. It could be on the whole real line, but certainly all x within a certain interval. You really have to check three things, and they're going to be specifically on the AP exam looking for you to check three things. The first thing that they are going to be specific that you have to check is, does the limit as x goes towards, and really let me back up, it's really as all x equaling some value c. So as x goes towards c, from the right side exists. So does the limit from the right side exist? Does the limit as x goes towards c from the left side exist? Does the function at c exist? And all of these, oops, my numbering is a bit bad there, here, 3 here, have to be the same. They all have to be the same. The limit from the left has to equal the limit from the right, and it has to be where the function is. If all those things are true, then the function is continuous. If any one of those things doesn't hold, the function's not continuous. So you have to check all four, and they're really going to be looking for you to check all four if they do it on an FRQ, or at least identify all four. It would be the kind of thing where maybe I'll show you an example. Let me do an example with a graph. Okay, so I'm just going to draw a graph, and a lot of times it's asking, show why it's continuous or show why it's not, why it isn't continuous. So let's say I draw a graph and it goes to here, and I'll put an open circle there, and let's say I go out of this and I redefine it right here. Now, graphically, if I said, is this continuous? Hopefully you guys would be like, no, that's not continuous. Of course that's not continuous. It doesn't look continuous. And you'd be right. But it might be something kind of be explain using the definition of continuity y f of x is not continuous when x equals 3. So that's what they'd be asking you to do. So that's where you have to go back and you have to have kind of these notes. So, well, what does this look like? Those four things have to exist, and they all have to be the same. So those top three things have to exist, and they all have to be the same. Well, if you kind of go break down these four things on this, and you kind of say, okay, well, let's look at the first thing. What is the limit as x goes towards 3 from the right side of f of x? And I'd say, yeah, that's 3. And I'd say, well, what's the limit? So the second thing, I'd say, what's the limit as x goes towards 3 from the left side of f of x? I'd say, yep, that's 3 as well. Consequently, from what we did yesterday, this means the limit as x goes towards 3 of f of x is equal to 3, right? I mean, so if the left side equals the right side, then they're equal. So the third thing is f of 3 is equal to 1. And I say, since f of 3 is not equal to the limit as x goes towards 3 of f of x, f of x is not continuous at x equals 3. So that's what I would say. That's how I would explain it. That's what you're going to be asked to do on the AP exam, is have this down. So, when we look at you look at open notes, that might be something I'd put on my open notes. I'd have some kind of consolidated notes. So when it says use the definition of continuity, that'd be something I'd definitely put on there. Some of the other things that sometimes show up, and I'm not sure where this will show up, if it shows up on the exam this year, would be an idea of a piecewise function. So let's look at a second example. And it might be something like this. Find k so that g of x is continuous. And it might be the kind of thing where g of x is defined as a function, maybe it's x squared when x is less than 2, and it's kx plus 3 when x is greater than or equal to 2. So the kind of thing, I guess, there's a formal notation on how you'd write this, and then there's a less formal one. So I'm going to do it pretty formally. Okay, so I'm going to use the definition of continuity. So one thing that we want to look at is what's the limit as x goes towards 2 from the left side of g of x? Well, that is 2 squared, or 4. Okay, so we know that the limit from the left side is 4. What we need to figure out is what's the limit as x goes towards 2 from the right side of g of x? That would be k times 2 plus 3. Okay, so we got a value of k in there that we're looking at. And what is g of 2? Well, g of 2 is also k times 2 plus 3 using our function. So that means what we need is we need k times 2 plus 3 to equal 4. If we need those things to be the same, that's what we need to have true. So that means we need k times 2 to equal 1. So that means we need k to equal 1/2. And if we get that, we're all good. So that's the idea behind continuity. So let me move on to this whole idea about the intermediate value theorem. Okay. Oh, let me back up one more thing. One more thing we kind of need to talk about, just so you know. They may ask you the idea behind removable or non-removable continuity. Removable continuity, really what you're going to look for is that is a hole in the graph. That's the kind of graph that looks like this. That's removable discontinuity. Okay? Non-removable discontinuity is either going to be a jump or an asymptote. So when something is not removable, that's the kind of graph that might look like this, whether these are filled in or not, or a vertical asymptote going to infinity. So one of those two things is really where you're going to get removable or non-removable discontinuity. So just put those down, because it, again, that's another piece of notes that you should have. Okay. So when I'm thinking about creating a document or having you kind of create a running list of things that you might want, right next to you when you're taking this exam, that's something I would have. We're kind of creating, we like to create a big old cheat sheet, something that you can use, something that's easily accessible. That's something I would have. Probably isn't going to have a lot of examples on it, because you're going to have to adapt the definitions to new examples, but that's something I would have. Okay. All right. So the last thing we're going to talk about today is the intermediate value theorem. IVT is the abbreviation of it. IVT has something specific. It says if a function f is continuous on an open interval a to b, then there exists a value c between a and b such that f of c is between f of a and f of b. So the idea behind this is that if we have a graph that's continuous, now that's kind of the stepping stone. If you don't have a graph that's continuous, intermediate value theorem doesn't work. If it does work, then it's the idea, we talked about it in class, where every y value between f of a and f of b is going to be hit. It's kind of, I referred to it at one point in time as the elevator theorem. If you start at level 4 in a building and you ride an elevator to level 16, you go through every floor in between. You would have to, because the elevator is a continuous thing. So Laura Thompson years ago kind of explained it that way to me in the whole class, and I said, that's a great way to explain it. So I really liked her explanation. The idea is if you have a graph, some function f that looks like this, and if you start here for A, and you go to even way out here for B, okay, so we go to here, here's f of A, and we go to right here, here's f of B. There's a value in here is some value C that corresponds, that goes with all the values between f of A and f of B. That's really what it says. You'll get some practice on that, some really good practice in delta math. That's it. I hope this is a little shorter video, but probably going to be on the exam. So let me know if you have any questions. I see some people have already actually done the problems on delta math, and good job. Let me know if you have any questions.